we go. Right, so now that you know how to name and write formulas for alkenes, let's talk about the properties of them. These are non-polar substances. Anybody remembers what is a polar and a non-polar substance? Any of you remember that? Hello?
They attract how much electrons they attract, I think.
These are substances that have a partial positively charged end and a negatively charged end. They are not like balanced in the charge. The charge is not equally distributed throughout the molecule. So the alkenes are non-polar. That means they don't have those endings, those positive and ending, because this is the polar substances. So they have the same properties of those in alkenes in terms of boiling points and physical states. That means, look at this example. Can anybody name this guy here? Can anybody name it? When it's 4 is tetra, we say tetra in. 2 is diene, 3 is triene, 4 is tetra in. Can anybody tell the name for this guy here?
1, 3, 6, 10, tetra.
Dodecane.
Remember that you don't name the longest chain first, but the branches. If you start here, you have a branch down here. This is just CH2. Have a next branch here, and you have a next branch here. Can you see that? So it's a
3,7,11 methyl trimethyl. No, yeah. 3,7,11 trimethyl. 1, 3, 6, 10 tetra. I mean, tetradoctene.
You say the name of the chain first, and then in the middle, right before, you say the tetra. Like, is it 11?
It's 12. So it's dodecatetraene.
Dodecatetraene. Okay, but that guy has a common name. By the way, let me tell you something. In life, many of the compounds that you use have a chemical name, like the aspirin that people use is just acetyl salicylic acid. The gasoline that people use is just octane. It's an alkane that has 8 carbons, octane. The rubbing alcohol that people use is isopropanol. This guy here has also a common name, that is alpha farnesene. Okay, this is solid at room temperature, and you can find it in the wax that they put on the apples. The natural wax that cover the apples contains this substance, alpha farnesene. Okay, and what is the point of this, of telling you this? Well, this is a solid at room temperature because it has a lot. Let me go back to that before we enter into the alkynes. Because Okay, it doesn't want to move back. All right. So you can basically use the same properties that you know that alkanes have and apply it to the alkenes. The first 4 or 5 are gases at room temperature. The next 10 compounds are liquid at room temperature, and after that they are solid at room temperature. Okay, so the alkynes, just to move on this, alkynes are those that have a triple bond, as you know. The difference between alkenes and alkynes is the type of bonds that they have. Okay, of course, the simplest one is the ethyne, 2 carbons. These 2 carbons are attached by a triple bond in between them, just like this. And then they both have just 1 hydrogen atom. So notice that now the number of hydrogens decrease even more. At first, when you have 2 carbons and it's alkane and it's an alkane, you will have an let me type it here. Let me put it here. If it's an alkane, you will have 3 hydrogens in every carbon because you have only a single bond. Oops. Because you have only a single bond. Now, when you have an alkane, I'm sorry, breaking up.
Can you repeat what you said?
Okay, sorry about that. My internet just hot. But I was telling you that the number of hydrogens now continues to decrease. In the alkanes, you have 3 hydrogens in every carbon for the case of the 2 carbon chain, right? Now, in the alkenes, you have only 2 hydrogens, and in the alkynes, it decreases even more, and you have only 1 hydrogen. Why? Well, the rationale of that is that you have 3 of the bonds of each carbon used here to bind the 2 carbons that you have. So you're only left with 1 more that you can fill up with hydrogen. Therefore, the general formula is this: CnH2n minus 2. The number of carbons that you have is you can double that number of carbon and then subtract 2. So if I tell you, for example, the hexane, how many hydrogens you expected to have? The hexane, how many carbons you think is going to have? Can anybody tell? If you apply this,
It would be doubled.
I'm sorry?
It would be doubled the amount of.
The number of hydrogen that you're going to have in the hexane, how much is it going to be?
10.
No, wait, yes, 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 it's going to be 10. Double minus 2. So it's going to be 10. You're right. Okay, it's the same. The procedure to name them is the same as the alkene. The only difference is that the ending in changes by "-ine". So this is not pentene, but pentyne. This wouldn't be 3-methyl-1-butene, but butyne, okay? And that's just because of the triple bond that you have there. That's the only difference between the alkenes and alkynes. Now, I'm not even going to give you examples on that because it's just the same thing. And yes, if you have more than one, you know that you can you can state it in the name. Okay, there is also what we have covered so far is just the aliphatic hydrocarbons. Now there is another set that these are the aromatic hydrocarbons. This one have a 6-carbon ring that looks just like this. This has a name, is a benzene. Whenever you have a compound that contains this structure, benzene is going to be an aromatic hydrocarbon. Vanilla, for example, is one of the compounds that contains this. And I'm pretty sure that you have witnessed the sweet smell that it has, haven't you? Yes?
Yes.
This is present in vanilla, this structure here. The actual name wouldn't be benzene if we use the IUPAC name. It has 1, 2, 3, 4, 5, 6 carbons. So it's going to be a hexene because it has double bond, at least one. It has 3. So the actual name, let me see if you can hear me to state it. What would be the name for this structure here? Can anybody tell?
The actual name?
Yes.
Hexatriene.
Hexatriene. But where are these 3 double bonds located? Because this is let me tell you, because this is a ring, this is a cycle. You have no such a thing as carbon number 1 or carbon number 6. So you decide where is your carbon number 1. I could say that this is carbon number 1, and then I have a double bond in carbon number 1. 1, 2, 3, another double bond in carbon number 3, 4, and 5, and another double bond in carbon number 5. So this is going to be 1, 3, 5 hexatriene. Now it's also a cyclo. Can you see that? Yes, because it's a ring, and I mentioned to you before that whenever you have a ring, you have to say cyclo and whatever is the name of the hydrocarbon. Okay, because if I just say hexatriene, probably you will do something like this. You will have a C and a double bond, then another C, and then another C and another double bond, another C and another bond, and then another C and another double bond, and then another C. 1, 2, 3, 4, 5, 6. There you go. You have your 6 carbons here, and you have the 3 double bonds. If I just leave it like this, this would be my formula. 1, I have a double bond in number 1. 2, 3, I have another double bond in number 3. 4, 5, another double bond in carbon 5. But because this is what I want people to understand, I need to state that this is a cyclo. Is that clear?
No.
Okay.
Yes.
And let me tell you something else. Even though if I decide not to start on this carbon, but start here, it's going to be exactly the same thing. Because if this is my carbon number 1, then I have to start counting on this direction. Okay, and I will have the double bond in carbon number 1, carbon number 2, and carbon number 3, and in carbon number 5. Now, if I decide to start counting not on this carbon, but on this, it's going to be the same thing. This would be carbon number 1, and then I have to move in this direction because I want my double bonds to have the lowest possible numbers. And in the cycles, in the rings, you not necessarily move counterwise or clockwise. It depends on where you have a very important item, and this is the direction that you will follow. So if I start here, I will count counterwise. If I start here, I will do it clockwise. And it doesn't matter where I start, my double bond is going to be in carbon number 1, carbon number 3, and carbon number 5. Is that clear? Do you understand what I'm saying?
Yes.
Okay.
Yes.
for people not to go through all of these and mention 1,3,5 cyclohexatriene, they just simplify the name for this and they call this benzene, as you can see here. This is the primary aromatic hydrocarbon, and this is a very common structure. Sometimes this is just the main chain, and then it might have branches here. Here you might have a CH3, and then that would be 1-methyl benzene. Whatever you have then a chain that will make that carbon the carbon number 1. For now, I can say that this is carbon number 1, but if I have a methyl here, CH3, then this would be carbon number 1. And I would say 1-methyl benzene. Also, let me explain something real quick about this, is that sometimes they draw the benzene like a hexagon, you know that? It's a hexagon. I'm sorry if it's not perfect. Okay, just stay there. A hexagon, and then they put a circle in the middle. This circle in the middle means that the double bond that you have here is not fixed in between these two atoms. Sometimes this double bond breaks off and then it forms here. And when that happens, this also breaks off and forms here, and this breaks off and forms here. So the double bond keeps rotating inside of the hexagon, okay? And that's why they draw it this way. So anytime you see a hexagon or a hexagon with a circle or this, you must know that this is benzene, the primary compound of the aromatic family, okay? Yes, is that clear?
Yes.
Okay, let's move on then. About the aromatic hydrocarbons, this guy doesn't behave as an alkene. Remember that this way is distributed, allows the electrons to move around, and then you can have the double bonds all over. Again, it's not in a fixed location, but it can rotate, and that's why they draw it with this circle inside. Okay, so this is what I mean. You can have the double bond on top here. What you will know is that they are not going to be in sequence. You will not have a double bond here and the next right there. That wouldn't happen. It's going to be a double bond, a single bond, a double bond, single bond. So they will be alternated. Okay. So the two possible structures are these: the double bond on top, and then to the sides, single bonds, double bonds here, and then a single bond here. Or that could also be single bond to the top and double bonds to the sides, single bonds here and double bond here. These double bonds are going to be rotating, okay? That's why they put this circle inside. Let's see how we can name the aromatic compounds. I don't want to go into this part, the functional groups. That's a whole different story. So I'm gonna pause the recording to pull up the rules on how to name the aromatic compounds. All right, so even though you know that the double bond could be here, there, here, it's much better if you draw the benzene ring with the circle inside, because that way you're stating that it could be anywhere, as we discussed before. So they follow the same naming rules that we learned before. If we have a branch here, then I would name this methylbenzene. This is just chlorobenzene. And this is, what would you name this? The one to the bottom. Hola. What would you name this structure here? Hola.
One ethyl.
Keep going.
1, 3, 5 cyclotrihexene.
Okay, remember, you can use the word benzene as part of the name. You don't have to go through the 1,3,5 hexatriene, cyclotriene. Just say benzene and it's accepted as part of the name. Okay?
Okay.
So what would be the name for this?
1 ethylbenzene.
Yes, that's it. 1-ethylbenzene. And sometimes it's accepted, even if you don't say 1. If you just say ethylbenzene, people will know that it's in carbon number 1. Okay? If you just say chlorobenzene, people will know that it's in carbon number 1. Because there's no way chlorobenzene is in other carbon than number 1. You hear me?
Yes.
Now look at this. Here, you don't have only one substituent. You don't have only one branch, but you have two. Notice that I'm just naming, that I'm numbering the chloro. The methyl remains in number 1, and I don't have to mention the number 1 for that. As you can read here, some of these molecules contain more than one substituent. In this case, you name the substituent in alphabetical order with the lowest possible numbers. Okay? So this will be number 1 because it's a branch. This is not a branch. This is just a halogen that is part of this, but this is not a branch. A branch is made up of carbon atoms and hydrogen. Okay? So we have carbon number 1 here, carbon number 2, and carbon number 3. So I name this, if I follow the alphabetical order, this is going to be chloro, 3-chloro, because the chloro could be in the 2, and the 4, and the 5, and the 6. Actually, it can only be in the 2, 3, or 4. It will never be in 5 or 6. Why? Can anybody tell me why it wouldn't be in 5 or 6? Any idea?
No, not.
Because of the group it's in.
Because
Do you feel like?
because the moment I put chlorine here or here, then I will count in this direction. Remember, it's not always clockwise. It could be counterwise. And if the chlorine is located here, then I will start counting in number 1 here where the methyl is located, but I will move so and not so. In this case, I'm moving so because if I move so, I will find the chlorine in a lower carbon than if I move so. Is that clear? You understand what I'm saying?
So,
Repeat that, please.
I need to know that everybody understands what I'm saying. I will repeat it. I will repeat it. Remember, it's not always clockwise that I'm going to move. I know that this is carbon number 1 because this is where I have the methyl. And methyl is a branch. So it's more important than chlorine because chlorine is not a branch. It's just an atom that might be attached to a chain like this one, for example. If I have this as number 1, I could move counterwise or I could move clockwise. In this case, I'm moving clockwise because chlorine is here and I want all of my substituents to have the lowest possible numbers. Okay, now if chlorine is located here, I wouldn't say that chlorine is in carbon number 6 because I wouldn't continue to count like this. I will start counting like this, and then chlorine is going to be in number 2. Do you understand that?
so other atoms that are not hydrocarbons have priority over double bonds?
No, the hydrocarbon has the priority, and that's why where I have the methyl here, this line is methyl, by the way, is a skeletal formula. The methyl is the one that has priority. That's why I'm not starting counting here. That's why chlorine is not in carbon number 1 and methyl is in carbon number 3. But methyl is in carbon number 1 because it has a priority. Chlorine is second place in the priority level. Is that clear?
Yeah, I think so.
Yes? Any questions? I don't want to move on if anybody has any questions.
Okay, just to clarify.
Uh-huh.
So the branches, a carbon branch has priority over atom of a different substance, right?
Yes, unless it's a functional group, and this is going to be discussed later. Okay.
Well, aside from that, it has priority over a atom from another
Yes.
thing.
Yes.
But the atom has priority over the double bonds.
No. No. No.
So if we put it in number 6, you would count the chlorine as number 2 and not the double bond as number 2.
Okay, but remember, the location of the double bond is not fixed. Remember that these double bonds are rotating. So
okay.
a double bond would be here then. You understand?
Okay, I get it now. Yes.
Okay. So this compound is 3-chloro, even though the methyl has priority over the chlorine, I still have to name it first because of the alphabetical order. The location of these substituents doesn't mean they have priority over the next. It just means that it has a letter that follows the alphabetical order. So I have 3-chloromethylbenzene. I don't state a number for the methyl because it's automatically in carbon number 1, as I mentioned to you before. Okay, so let's practice this. And I'm going to tell you something. We have only 7 minutes. But when you have two atoms that are one next to the other, there is a way to say 1,2. This is the same thing. 1,2 dimethylbenzene. Let's draw this. How would you draw this? How would you draw the 1,2 dimethylbenzene? Can anybody tell? What is the first thing that you would draw?
The hexagon?
Yes, exactly. The benzene. Okay. And where would you place the two methyls here? In 1 and 2. What is carbon number 1 here? Whatever you decide it is. So it could be here. But if this is carbon number 1, carbon number 2 is going to be either this or this. It doesn't matter because you can count clockwise or counterwise. So let's say that is here. There you go. One, 2 dimethylbenzene. Also, you can refer to this as, I'm gonna tell you this later because I don't have a lot of time for that. We don't have enough time for that. All right. What would you name this guy here? What would you name this guy here? The one on top. Hola. We only have 5 minutes. What would you name the first guy here?
1,2. Just 2 bromine or
Bromo, bromo, bromo.
bromo,
Uh-huh.
1 metal benz.
Yes, 2-bromo methyl benzene. Remember, you don't have to say 1 for methyl because it's implied that the methyl is in carbon number 1. So 2-bromo methyl benzene. How would you name this one? A girl? Let me hear a girl. What's the name for this one? Hola. Is any girl alive? Okay, anyone? Hello? We're running out of time. What would you name this compound here?
To be honest, I'm not sure.
1,4 dichloro
Chloro, benzene.
benzene. Oops, sorry.
But there-
Dichloro benzene. Any questions on why? Well, you have 1 in carbon number 1. If this is carbon number 1, you count 2, 3, and 4. So 1,4 dichloro, because when you have the same kind of substituent, you can group it. And then it says no 1 chloro, 4 chloro, you say 1,4 dichloro, and that's it. All right. How about this one here? Let's name this one here. What is carbon number 1 here?
Metal. Metal.
The methyl is, okay. So what is the name for this? Remember to respect the alphabetical order. That's what I want to tell you.
3, chloro. No, 3,6 chloro.
5, amigo.
5. I don't know, I can't count.
Mhm.
5 chloro. Metal benzo.
Excellent. Excellent.
Benzene.
Excellent. Very good. Very good. Good job. 3,5 dichloromethylbenzene. All right. Before we finish, girls, can you help me to do this one? This one. I'm not gonna ask you to do this one to the bottom, the one to the bottom, because it's very complicated for you. But this one, number 3. Let's do the hexagon first. Yes, because these are aromatic compounds. They all contain the benzene. Okay, where do you want me to place the methyl or the ethyl?
Those can be placed anywhere, right?
I'm sorry?
Those can be placed anywhere, right?
Yes, the first of them can be anywhere.
Okay.
Okay, where would you place the ethyl now? This is the methyl.
To the right.
Okay, right here.
Yeah.
If I place it here, this would be 2 ethyl, because this is number 1. The next is number 2. So I can't put it there. Where do you want me to put it then?
Oh, the bottom right.
Yes. And because it's an ethyl, I have to do like 2 lines. And that's it.